Hello everybody, this is Mr. Strager back again with some Big Ideas notes. Today we are talking about section 2.2 in our inequalities unit. Now, I mentioned last video that unit 2 looks very similar to unit 1, and the similarities don't just stop in the first section. Here, we are going to start off by talking about equivalent inequalities. Just like how we had equivalent equations in unit 1, equivalent inequalities are a way for us to determine whether or not we're talking about the same solution, just in different forms. That is to say, an equivalent inequality, or I should say equivalent inequalities, are inequalities that have the same solution. Inequalities that have the same solution. Let me give you a brief example of one. Let's compare the inequalities. X is less than 3, and x is less than 1 plus 1 plus 1. Well, we know that these two are actually going to be the same, because 1 plus 1 plus 1 is just 3. It's another way of putting 3. Both of these have the same solution. Both of them are going to show us lines, or I should say rays, that don't pass through 3, but definitely start there, and go off towards lower numbers, like 2, 1, 0, -1, -2, and so on. These two inequalities have the same solution. You may recall something that we did in Unit 1 seeming pretty similar to this, to be honest with you. The difference was, back in Unit 1, we had equations that looked like this. X minus 3 is equal to 5, for instance. And we wanted to produce an equivalent equation where x is by itself. Well, it turns out the goal is the exact same for this unit. We want to produce an equivalent inequality where x is by itself. How did we do it back in Unit 1? How would we get x by itself in a problem like this? Well, to get x by itself, we need to get rid of everything that's attached to it. We're looking for what's attached to our x. And, well, there's only really one thing that's attached to our x. This minus 3. How do we get rid of minus 3? Well, we would use inverse operations to get rid of it, to cancel it out. So I would add 3. The problem is that this wouldn't produce an equivalent equation. To produce an equivalent equation, the rule was, whatever you do to one side, you have to do to the other. So we would add 3 to this side as well, giving us our solution, x equals 8. This rule was the addition property of equality, where you're allowed to add something as long as you do it to both sides. Turns out, the exact same rule applies for inequalities. As long as you do it to both sides, you can add whatever you want to both sides, and it'll produce an equivalent inequality. Let me give you an example. If I had 0 is greater than -5, yes, that is a true inequality. 0 is less than -5. If I wanted to produce an equivalent inequality, well, let's say I added 10 to both sides, just because I wanted to. Again, we had to do it to both sides. Our inequality symbol is going to stay the exact same for this section. 0 plus 10 will give us 10. -5 plus 10 will give us +5. Is this an equivalent inequality? Is 0 is greater than -5 equivalent to 10 is greater than 5? It may not seem like it, but yes, these say the same thing. These just say a statement of fact. Of course, something like this we could just do forever with whatever number we want. It doesn't actually give us a simpler equation, though, or inequality, I should say. Instead, what if I gave you a situation like this? X minus 3 is greater than 5. Well, notice that this looks very similar to the problem we just did up here. We want to get x by itself because that's the solution of an inequality. Our solution is when x is by itself, it'll tell us all the things x can be. How do we do it? Well, just like in the last example, we notice that we want to get x by itself, and what's attached to our x? This minus 3. How do we get rid of minus 3? Well, we add 3 to both sides of our inequality. There's our dividing line, and there we go. What's negative 3 plus 3? Well, they cancel out. It gives us 0. That's the reason why we chose 3, is because it'll cancel it out, giving us x all alone. We keep the inequality symbol the exact same. Then 5 plus 3 will give us 8. So our new inequality, our solution to the inequality, is x is greater than 8. Is this a fact? Let's test it out. Our original equation was x minus 3 is greater than 5. So let's pick a number that's greater than 8 and see if it works. Well, 9 is greater than 8. It's the closest integer that's greater than 8, so I'll just pick this one. 9 minus 3 will give us 6, still the greater than symbol, and our 5. Is this true? Yes, 6 is greater than 5. So that tells us that the inequality actually ended up working out. Our solution is x is greater than 8. This is a thing that we'll have to keep in mind throughout this entire unit. Just like Unit 1, to get x by itself, we want to do the opposite to both sides of whatever's attached to it. Of course, you may have predicted that if there's an addition rule where you can add something to both sides, it only makes sense there's an equivalent rule for subtraction. Let's take a look at it. The subtraction property of inequality. If you subtract something from both sides, you'll get an equivalent inequality, just like how we did with equations. Let's give this one a test as well. X plus 20 is less than or equal to 50. Again, we want to get x all by itself. So we have to do the opposite of whatever's being done to it on both sides. Well, what's being done to it? We're adding 20. The opposite of adding 20 is subtracting 20. And our rule says we can subtract whatever we want as long as we do it from both sides. So we also have to do 50 minus 20, giving us x all by itself is less than or equal to 50 minus 20 gives us 30. Let's flip the page just one more time. Let's take a look at a problem like number 3. Because with these problems, you will need to be able to graph your solutions. Number 3 gives us s minus negative 1 is greater than or equal to 2. In order to solve this problem, we need to consider the following. So, with this problem, we are going to address it sort of the same way that we've addressed the previous ones. Of course, the problem is we don't actually have any numbers on our number line yet. Let's hold off on that for a second. Let's take a look at the problem. S minus negative 1 is greater than or equal to 2. Our goal is to get the variable by itself. So we need to look at what's attached to our s. The thing that's attached to our s is this minus negative 1. Now, negatives can scare a lot of people, but as long as you remember the steps, it will tell you what you need to do. To get rid of subtracting negative 1, we do the opposite. The opposite of subtracting negative 1 is adding negative 1. Of course, we've got to do this to both sides. Once we do this, these negative 1s will cancel out, and we're left with s is greater than or equal to 2 plus negative 1, which is the same as 2 minus 1, which is just 1. In order to graph our solutions, we first need numbers on our number line to help us with this. My recommendation is always to get your endpoint first. Figure out where your line is going to start and end so you know you have enough space for it on your graph. Here we have one endpoint. It's at 1. And is it a closed circle or an open circle? Well, it's equal to. So it's going to be a closed circle. This bar underneath means that we are going to have a closed circle. When we make our scale for our graph, we want to put our endpoint somewhere around the middle, just so we're able to see sort of the whole line unfold. So we're going to put a 1 here. Well, what are we going to fill into the left of the 1? The left of a number line goes down, so we're going to count down into the negatives, to negative 4. On the right side of 1, we would count up, 2, 3, 4, 5, 6. What this means is that we always have to have our number lines facing the same way. If you were to have your negatives all the way over here and your positives all the way over here, your number line would be flipped and the arrow would point a different direction. To make sure that it's pointing in the right way, you need to make sure your numbers are going in chronological order from least to greatest. So, as we mentioned, our endpoint is at 1, and because it has a bar underneath, it's a closed circle. To decide where our line is going to go, or our array I should say, let's plug in a number for s, any number. If the number we plug in works, our arrow will point in that direction. If the number we plug in doesn't work, our arrow will point in the opposite direction. So let's plug in, let's do 0. If we plug in 0, we get 0 is greater than or equal to 1. Is that true? Well, no, 0 is not greater than or equal to 1. It's less than 1. So our arrow is not going to point in the direction that'll cover 0. 0 is on the left, so our arrow must point the other way, to the right. The last problem type you will see are problems like this, word problems. And any time you have a word problem, I would highly, highly recommend using the rough draft math method. Don't worry about finding an answer yet. Just worry about interpreting the information and getting it written down. Problem is this. You have $15 to spend on groceries. You have $12.25 worth of groceries already in your cart. Write an inequality that represents how much more money, M, you can spend on groceries. Here's the deal. We need to figure out what piece of information we're dealing with. So I'd like you to pause the video and just write down in the margins any information that you think is mathematically relevant. Some pieces of information that you might find mathematically relevant are this. You've got $15 to spend. So we're going to have to use 15 at some point. We already have $12.25 worth of groceries in our cart. So of that 15, we've already used $12.25. The other thing we have to consider is our variable. Our variable represents how much more money, M, you can spend on groceries. The rough draft method, you need to be able to figure out what you're trying to figure out and the pieces of information that are attached to it. We're trying to figure out M, how much more money we can spend on groceries. We're given that we have $15 total and that we use $12.25. The problem is, this doesn't have any operations in it. We don't have any plus, minus, multiplication, division. It's sort of hard to tell what the operation is going to be. This is where we need to start thinking about the inequality itself. So, here's a question for you. Inequalities are always going to compare things that are greater than, less than, or equal to. In this case, what is the greatest thing we have? What is the biggest quantity we know? Well, we know that we only have $15. That's it. Even with this $12.25 and this M, no matter what, $15 is our absolute limit. Is 15 bigger than the rest, or is it smaller than the rest? Well, for this one, we know that 15 is going to be bigger than the rest of our problem. What that means is we're at least going to have this symbol here. It might be an equal sign as well. Who knows? But for right now, this is the symbol we're putting in. That means everything else is going to be on the other side. We're going to include this $12.25 over here and this M. Now let's think about this. If we already have spent $12.25 on groceries, and M is how much more money we can spend, then what do we do between these two? Would it make sense, for instance, to multiply the amount of money we spent by the amount of money that we still have to spend? No, it doesn't quite make sense. Would it make sense to subtract what we have spent from the money that we have left over? Well, no. The money left over is going to be left over after we already spent this. So it would make sense to subtract it from there again. But then we think to ourselves, aha, the amount of money I spend on groceries has to be at least less than, possibly equal to, $15. The amount of money that I spend is $12.25, as well as how much more money I spend. You can think of them as being added together. $12.25 plus whatever else I spend has to be less than 15. But here's a question for you. Could it also equal $15? Well, in this situation, it makes sense, yes. If you have $15 to spend, and you spend $12.25, you can spend as much as you can until you reach that $15. If you get something that's exactly worth enough to make this side go to 15, then I consider that a successful shopping trip. It's not just less than 15 is not just greater than the rest. It's greater than or equal to the rest. So this is our inequality. 15 is greater than or equal to 12.25 plus M. Now we just need to solve it. To solve this inequality, we have to consider what we're trying to get by itself. In this case, we want to get our variable M all by itself. Well, what's attached to our M? This plus 12.25. So to get rid of adding 12.25, what can I do? I'm going to subtract 12.25. That'll cancel it out and get the M by itself. But whatever you do to one side, you have to do to the other. So these will cancel, and we'll end up with 15 minus 12.25. 15 minus 12.25 will actually give us 2.75. Our sign is going to stay the exact same, and our variable is what's left over. 2.75 is greater than or equal to M. If you want to interpret it differently, you could also flip it around. You could say that M is less than or equal to 2.75. Both of these are equivalent. But what does this mean in the context of the problem? Anytime you have a word problem, Your answer should be words. Well, what is the unit that we're trying to use for M? It's money. And since we've used dollars throughout the problem, it only makes sense that 275 is $2.75. To finish off this problem, we say we can spend up to $2.75. And these words up to says that I can spend less than $2.75 or equal to $2.75. That represents this inequality here. Thank you so much, everybody. Have a fantastic rest of your day.